Welcome to Manufacturing Processes, Machining and Machine Tools lectures by Professor Joyjeet Ghose. This is the second lecture of a series of lectures. This lecture will be on mechanics of orthogonal metal cutting. He will be discussing about chip thickness ratio, shear angle, forces acting on the tool, forces acting on the chip, Merchant's circle diagram and force relationship in metal cutting. So, do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access my videos. Please subscribe my channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to lecture 2. In this lecture, we'll be discussing about the mechanics of orthogonal metal cutting. So let's get started. In the last lecture, we have discussed about the how a metal cutting, how material is removed, or the model of the metal cutting as presented by Eugene Merchant. So here in that particular model, that is the model which we'll be following in order to study the mechanics of orthogonal metal cutting. In that model, during the metal cutting, the metal is severely compressed in the area front of the cutting tool, and when the stress exceeds that of the yield strength of the workpiece material flows plastically in the form of chip over the cutting tool face. So the outward or shearing moment of each successive element is arrested by work hardening and the moment transferred to the next element. The process is repeated and the continuous chip is formed. This is considered to be a ductile material. The model is considered for a ductile material. In brittle material, something different happens. That we'll discuss later. Now, before we move on, there are some assumptions that we have to take into account in order to study the mechanics of orthogonal metal cutting. These assumptions are: no contact at the flank side. That means the tool is perfectly sharp. There is no contact at the flank side. So if this is the flank side, and this is at a point. There is a zone, but we'll consider it as a point. So there is no contact on this side. So that is one of the assumptions. No side flow of chips. That means the chip will flow perfectly over the face of the tool, and not on this side or not on this side. So this is one other assumptions. Uniform cutting velocity, which is very difficult to achieve. Continuous chip is produced with no built-up edge. What is built-up edge we'll be knowing later. So just understand that there is a continuous chip which is produced. The work material undergoes deformation across a thin shear plane. So this plane is a thin shear plane, and we consider it to be a straight plane here. And there is uniform distribution of normal stress and shear stress. So the shear stress along this plane and the normal stress along this plane are considered to be uniform. There is no localization of the stress. The depth of cut is constant. So there is a constant depth of cut. Depth of cut, in this case, it will be the width. The width remains constant. In other words, the width remains constant. The cutting edge is lying perpendicular to the direction of motion and generates a plane surface as the work moves past it, or as the tool moves past it. So this is considered to be a perfectly straight. So these are the assumptions. With these assumptions, we'll again come back to the model as was presented by Eugene Merchant. There is a tool, there is a workpiece, and the chip is moving in this direction. The rake angle is alpha. The angle with which it is inclined away from the workpiece is called the rake angle. So this is the shear angle that I have discussed in last class. This is the shear plane, and okay, this is a positive rake angle. Rake angle, had this plane be in this direction, it would have been negative rake angle. So this is a positive rake angle. Therefore, the negative and positive is given here. Okay, now this is the shiny surface will be on the lower side of the chip because it rubs over the face of the tool, and the rough surface will be on the top of the chip. And this thickness is called the chip thickness, and this thickness is called the uncut chip thickness. This is represented by T0, this is represented by TC. TC is chip thickness, T0 is uncut chip thickness. So what is rake angle? The angle of inclination of the cutting tool or tool face from the reference plane, that is the plane perpendicular to the velocity vector VC. So the velocity vector VC is in this direction. So perpendicular plane to this, and this angle is called the rake angle. So clearance angle is the angle of inclination of the clearance or flank face of the tool from the finished surface. So this is the clearance angle. Now this is TC and this is T naught. So if the rake angle decreases, chip thickness increases, shear angle decreases. Okay, so there is a relationship between the rake angle, shear angle, TC and T naught. We will find out that relationship. Okay, so this is thin chip, thick chip, short shear angle and large shear angle. So what happens? Just go through this figure. This is the figure which appeared in my book, tool design. Just go through this diagram, you will understand. Okay, so we'll move on to find out the chip thickness ratio T naught. A parameter has been defined, chip thickness ratio. Chip thickness ratio is ratio of the uncut chip thickness to the chip thickness. Now uncut chip thickness is T naught and chip thickness is TC. So R, the chip thickness ratio R, is defined as T naught by TC. T naught by TC. Now if we consider that the width of the chip remains constant, then we are compressing it. So once we are compressing it, the width remaining constant, the length of the chip will increase, or length of the, since we are compressing it, the length of the chip will decrease. So if the length of the chip decreases, this dimension, that is the thickness, will increase. You are compressing it, the length decreases, thickness increases. So obviously when you are metal cutting, TC will always be greater than T naught. TC will always be greater than T naught. So therefore the chip thickness ratio R will always be less than 1. It will always be less than 1. R is ratio of T naught by TC. So TC will always be greater than T naught, and therefore R will always be less than 1. Now R I can measure from the metal cutting process. If you take the chip and you can measure the thickness of the chip, T naught, we know this is a set parameter for metal cutting. In case of lathe machine, T naught is the feed. In case of other processes like shaper machine, planer machine, T naught is the depth of cut. I repeat, T naught is the feed in case of lathe machine. Why, you will know later, I will explain later. Right now just remember that T naught is the feed in case of turning. In case of shaper and planer, T naught is the depth of cut. So I can measure TC, I know my T naught, so I can always measure the chip thickness ratio. The problem is that I cannot measure the shear angle phi. It is extremely difficult to measure the shear angle phi. We have to cut a piece from it and scan it in the scanning electron microscope to take the image of that, and then you can measure the shear angle, so which is extremely difficult. So we want an alternative method, or analytically we want to find out the shear angle. The shear angle can be found out, we will find out a relationship of the chip thickness ratio R and the rake angle phi. Okay, now in this diagram, this is T naught, this is TC. So let's say this perpendicular is also TC. If I draw a perpendicular from this point to this point, it is TC, and I'll draw a line parallel to this line, which will intersect at this point. Now this is 90 degree, this angle is alpha, so this is 90 minus alpha, and in this triangle, this is perpendicular, this is perpendicular since I have dropped perpendicular from here, and this is equal to TC. So this is 90 degree. If this angle is 90 minus alpha, so this angle will be alpha. If this is alpha and this is phi, this angle will be phi minus alpha. So with this knowledge, we can find out a relationship of shear angle phi in terms of TC, T naught, and or R and alpha. So R is given as T naught by TC. So this is TC TC is nothing but if I represent this, if I represent this as LS, which is the length of the shear plane, then LS sine phi will be T naught. LS sine of this angle will be T naught. Similarly, LS cos of this angle will be this perpendicular, which is TC. So LS cos phi minus alpha will be equal to TC. So LS will become R. We know that sin phi by cos phi minus alpha. If you manipulate it, if you simplify it, you can find out tan phi is equal to R cos alpha by 1 minus R sin alpha. Try it yourself. You can find it out very easily. Just expand this and then rearrange, and you can find out tan phi is equal to R cos alpha by 1 minus R sin alpha. So I wanted the relationship of phi in terms of R and alpha. We have derived it. So now if I can measure R, I know alpha of any tool. So I can find out the rake angle of any tool as known to me. So I can find out this shear angle phi. Now the velocity relationship. The velocity with which it is moving about the shear plane is called the shear velocity. This is the cutting velocity, and this is the frictional velocity, the velocity with which the chip is moving over the tool face. So that is the frictional velocity, this is the shear velocity, this is the cutting velocity. So these all three are in equilibrium, and we can consider a velocity vector triangle like this: VC, VS, VF. So this angle is alpha. So this angle will be 90 minus alpha. This is phi. So if this is phi, 180 minus 90 minus alpha minus phi will give you 90 minus phi minus alpha. So using Lami's theorem or sine rule, we can find out an expression of VC, VF, expression of VF and VS in terms of VC. We know the VC because we will be setting the cutting velocity. So VC is known to us. VF and VS we can find out from this relationship. So the VF is equal to VC sin phi by cos phi minus alpha, and VS is equal to VC cos phi cos alpha by cos phi minus alpha. So this you can find out. So cutting forces, very important. Cutting forces are very important for us to know for proper designing of the cutting tools, for proper designing of the fixtures, for calculation of the power that is required, and selection of cutting forces. We have to know the cutting forces. So how do we find out the cutting forces? We find out the cutting forces, we can measure the cutting forces real time using an instrument which is called tool force dynamometer. Now let us see what are the cutting forces that is applied by the tool on the workpieces. So here, this is an orthogonal cutting that is going on. So as the tool is rotating, the cutting force is acting on the tool in perpendicular direction. This is called the cutting force, which is the largest force that is acting on the tool. So this is the cutting force. And as we are moving in this direction, the work is applying a thrust force in this direction. This is called thrust force or feed force. As the tool is fed in this direction, another force is acting in this direction perpendicular to FC, which is called the feed force or thrust force. FT, we will represent it by FT. This is FC and this is FT. Now radially a force will be applied by the workpiece on the tool, that is called the radial force, FR. In orthogonal cutting, FR we consider to be a minimum and 0, and if it is perpendicular, then FR we can consider to be 0. So in this case, in orthogonal cutting, there will be two components of force, FT and FC. FC is the largest, followed by FT and then FR. Now if FR is 0 or very less, we can safely consider that the metal cutting process to be an orthogonal metal cutting. And all the three forces are mutually perpendicular to each other, and the resultant force is acting in this direction, that is F, or we will represent it by R. So in orthogonal cutting, two components of forces are acting, FT and FC, and in oblique cutting, three components of forces, cutting force, thrust force and radial force. So you can see as the tool is rotating, this is the cutting force that is acting. As the tool is moving in this direction, this is the thrust force that is acting. Cutting force is acting on the tool as the tool is rotating, and over the tool, and the work is rotating over the tool. FC is acting in this direction, and as the tool is fed, FT is acting in this direction, and the radial force is acting in this direction. The tool, the cutting is, that is the resultant force is acting in this direction on the tool. So you can see the forces of all the forces. Cutting force is the maximum, this is the feed force, and this is the radial force, and this is the effect of the top cut and feed on the different types of forces. Okay, I have said that in turning, the depth of cut is equal to T naught. I will explain how. Now, this is the workpiece. This workpiece is rotating, and the tool is fed in this direction. So, FC is acting in this direction, FT is acting in this direction. The cutting edge is perpendicular, so the radial force is 0. This is a case of orthogonal turning. Now, this is the case of orthogonal turning. Now, in each rotation, the tool moves a certain distance, which is given as T naught in this case. So this is your feed. So in one rotation, the tool moves in this direction. This is the feed, which is equal to T naught. So in turning, T naught is equal to feed. So this is the chip thickness TC, this is the T naught, and this is W, this is the width. Width is considered to be remaining constant. So this part, if I reproduce this here, so this is the wedge shape tool which engages into the workpiece. So this is the feed as we move in this direction. This is the feed. This is equal to T naught, that is the uncut chip thickness, and this is the chip thickness here. This is the chip thickness, and this is the width of the chip, which is considered to be remaining constant. Okay, now the forces that are acting on the chip, till now we have discussed that the forces acting on the tool. Now these forces FC and FT I can measure by using an instrument called tool force dynamometer. I can measure real time during machining FC and FT. Now the forces that are acting on the chip are the frictional force system and the shear force system. That is frictional force F normal to the frictional force N, the shear force Fs, and the normal force Fn. Now all these four forces I cannot measure. These are the forces that are acting on the chip. Now I can express each of these forces in terms of FC and FT, and that is what exactly we will be doing. I will be expressing Fn, Fs and Fn in terms of FC and FT, and that the method of finding a relationship was given by a person called Eugene Merchant. He used a circle which is called Merchant circle diagram, which we'll be discussing next. Now for the time being, let us see what is the forces, what are the forces that are acting here. Now, as the tool is shearing the workpiece, and the chip is moving up due to shearing, the shear force acting on the chip, mind you, this is acting on the chip, will be in this direction, that is Fs. And the workpiece will apply a normal force as the chip tries to move up. The workpiece will apply a force Fn to the chip in this direction, perpendicular to this plane. Now it is assumed that this Fs is uniform across this plane and this Fn is uniform across this plane. Now as the chip moves up, the chip experiences a resistance force, that is the frictional force, in this direction, and the tool applies a normal force on the chip in this direction, that is represented by N. This angle is the friction angle beta. This angle is the friction angle beta. Now Fc is acting in this direction, Ft is acting in this direction on the tool. This is Fn, Fs and Fn are acting on the chip. Fc and Ft are acting on the tool. Okay, so it is assumed that the resultant of these two force systems are equal and collinear. And the chip is held under equilibrium under this two force system, and it is considered that Fs, vector Fs plus vector Fn is equal to R equal to vector F plus vector N equal to vector Fc plus vector Ft. Okay, M. Eugene Merchant presented a circle of finding out the values of Fs, Fn, F and N in terms of Fc and Ft. So how we have done, we will see. So the procedure for construction of Merchant circle diagram is that take a graph paper, you know you have measured the Fc and Ft, plot the Fc and Ft perpendicular to each other. Now join the ends like this. So this will be the resultant, obviously. Now with half the resultant and center of R from here, if I draw a circle, now this is perpendicular, so obviously the circle will touch the three corners like this. Now I know my shear angle. This I have drawn for you to understand. This is not required, but I have drawn to understand so that you will be able to understand. If I know my shear angle from this point, if I draw a line at an angle phi from FC, it will move in this direction. The point it will touch here, sorry, first let me discuss the frictional step. So I know alpha. If this is alpha, this is also alpha. So if I draw a line at an angle alpha, it will intersect at this point and it will cut here, and I drop perpendicular from here to here, that will be my n. So I can measure f and n. I can also measure angle n. This is a graphical method. This is a graphical method. This we are doing in a graph paper. Similarly, at an angle phi, if I draw a line, extend it, it will intersect at this point. So from this point, if I draw a line here, obviously this should be perpendicular because this is at 90 degree and it should touch here. Okay, so Fn. So I can measure Fs and Fn from here. So this is the graphical method which was presented by M. Eugene Merchant. So the resultant of all the force system is of course R. Okay, now we'll do the analytical method. We'll find out the analytical method. Now, if I draw the frictional force system here, just this part separately. Now, this is F, this is N, this is R, and this is FC, and this is FT. If I draw a line parallel to AB, OD, okay, and I draw perpendicular from B to C here on OD, and from E to D on OD, okay. Now, if this is alpha, this will be 90 minus alpha because this is 90 degree. If this is 90 minus alpha, this has to be alpha. If this is alpha, this is 90 minus alpha, and this has to be alpha. Okay. Once this is done, and if this is alpha, this has to be beta minus alpha because this is beta. Now we can find out the values of F by resolving the forces, and F comes out to be this value and N comes out to be this value. And when I know F and N, I can find out the coefficient of friction, that is equal to 10 of the friction angle beta. So similarly, if I resolve or separate the frictional force system Fs, this is Fs and this is Fn and this is Fc and this is Ft, I can express Fs and Fn in terms of Fc and Ft. So this is what we have done here. You can go through these deductions here. Okay, power that is consumed in metal cutting. So the power consumed in work done is Fc into metal cutting is basically Fc into Vc, and the power consumed in shearing is equal to Fs into Vs, and the power consumed in work done in friction, overcoming the friction, is F into Vf, where Vf is the velocity of the friction. The total power supplied is basically work done in cutting plus work done in feeding. So the work done in cutting is equal to Fc Ft, and this will be work done in feeding is equal to will be Ft into feed velocity. Now the Ft being very less, so this we can neglect, and we can say the total power supplied can be approximately equal to Fc into Vc. So I can write Pc is equal to total power that is supplied is basically used in shearing the metal and overcoming the friction. So Pc can be written as Ps plus Pf. So there is a term called specific energy. Now the specific energy is basically the total energy that is required to remove unit volume of material. So this specific energy is Fc by width of the cut, and T0 is the uncut chip thickness. Now this specific energy gives us an idea how easily we can cut a particular material. So there are tables available that the energy required for cutting different materials. So from this table we get an idea what is the energy required to cut the particular material. So this is very important from that point of view, specific energy. Now we'll move on to the theory that was provided by Ernst and Merchant. Now it is very difficult to find out the shear angle phi by measuring the chip thickness ratio and all these things. So Ernst and Merchant wanted to find out the relationship of phi in terms of the rake angle and the friction angle beta. And he made certain assumptions that is mostly the same as the assumptions of orthogonal metal cutting. The tool is perfectly sharp. The work material undergoes deformation across a very thin shear plane, and there is a uniform distribution of the normal stress and the shear stress of the shear plane. The work material is rigid and perfectly plastic. The work material is rigid and perfectly plastic means it does not undergo any kind of deformation until and unless it reaches the yield point, and after which it flows plastically, continues to flow plastically. So that is a perfectly rigid plastic. Shear angle phi adjusts. The angle phi he has assumed adjusts itself so that the minimum amount of work is required to cut the metal. The friction angle beta remains constant and independent of phi, and the chip width remains constant. So these are the assumptions that merchant has assumed in order to find out this relationship phi is equal to pi by 4 minus half of beta minus alpha. Okay, now let me express it in this manner. So this is R, this is the merchant circle diagram, this is the rake angle phi alpha. So this is total angle is 90 degree. If this is phi, okay, and this will be 90 minus beta, this is phi. So this total angle is 90 degree. If this total angle is 90 degree, so 90 minus phi minus 90 minus beta, sorry, pardon me, this total angle is 90 degree, this angle is 90 minus beta, so this is 90 minus beta 90 minus, this angle will be 90 minus beta minus alpha will give you beta minus alpha. This angle is beta minus alpha. So this total angle will be phi plus beta minus alpha. The phi plus beta minus alpha. So if I represent R in terms of Fs, if Fs will be equal to R cos of this angle, or R is equal to Fc sec of R is equal to Fc sec of this angle. So Fs will be this. So the shear stress will be Fs by As. As is the area of the shear plane. As is the area of this shear plane. This area, this length into the width. Okay, this area into the width, that is the shear plane. So As is equal to W T naught, W into T naught by sine phi. This area, if I project it, this area is W into T naught. So if I project it, so I'll get the area. So this is Wt naught by sine phi. So if I put it here, so shear stress is given as this. Now one of the assumptions. Now what are the constants here? Now these are Fc. This term, this is a constant term, and these are constant terms. So this I can neglect, and I can write y is equal to cos phi plus beta minus alpha and sine phi. This is the only variable here. So I want to optimize this one. So this variable I have taken and it is assumed that phi adjusts itself to give minimum work. So I'll differentiate y is equal to this, and differentiating equating to 0, we can find out phi is equal to pi by 4 minus half of beta minus alpha. So this is the theoretical calculations or expressions that Merchant found out along with Ernest in 1944. Now experimental validity shows that the above equation is an overestimate, and later another theory was provided by Merchant, that is called Merchant's second theory of metal cutting, which gives phi 2 phi plus beta minus alpha is equal to constant, which is not included in the syllabus, so I am not discussing. So this is very important theory in metal cutting, one of the fundamental, one of the first theories of metal cutting. Later on, many people has given many theories of metal cutting, but still this was the first and the most fundamental of theories given in metal cutting. Shear stress in metal cutting. So basically you will be shearing it here. The shear stress, the material from this point will be sheared to this point. Okay, so we can find out the expression in this manner. You can go through it self-explanatory. We can find out shear stress gamma is equal to cos phi cos alpha by sine phi cos phi minus alpha. temperature also plays an important factor. This is the temperature plot. How much temperature? 700 degree I think is the maximum. Again, it depends on the type of material and tool material combination and the cutting speed. Many factors are associated with the temperature distribution. So these are the graphs. You go through these graphs. Thank you for